Okay, in my previous video, I discussed discriminant analysis with SPSS, and basically I gave an example where my dependent variable was intention to donate money to a political cause in the near future, and then I had a set of predictor variables, which was political interest, dogmatism, and external political efficacy. Now, keep in mind that with discriminant analysis, what we're basically trying to do is to create a model that does a good job in terms of predicting group membership on a dependent variable based on what we know about scores or observations on a set of predictor variables. So the procedure itself requires that your dependent variable is categorical. Generally, it will fall at a nominal or an ordinal level of measurement, and the predictor variables in the model are falling at an interval or ratio level of measurement and generally assumed to exhibit multivariate normality within your groups. So, basically what I did when I ran the analysis, I just basically went through analyze, classify, discriminant. Basically, I put my dependent variable into the grouping box, indicated my minimum and maximum values on the dependent variable. In this case, I only had zeros and ones, and then I put my predictor variables into the model, and I went through a series of options and ran the analysis, and essentially walked you through describing the relationship between the discriminant function, which is basically a linear composite variable, if you will, based on the set of predictor variables. So it's a derivative of the pattern of associations among your predictor variables, and we looked at that variable in relation to our grouping variable. And so we looked at the canonical correlation, we looked at a significance test, testing that association, and then we went about the business of naming our discriminant function based on our structure matrix and standardized canonical discriminant function coefficients, and then further evaluating model fit, looking at the classification table. So in this particular illustration here, like I said, I want to look at a situation where we have more than two groups, because in this case we're going to have actually more than a single discriminant function that may be producing group separation with respect to our predictor variables. So what I've done is I've taken my political interest variable, which we had treated as continuous previously, and I basically chopped it up into thirds, or roughly thirds. So basically a value of 1 is associated with a person who falls in the low levels of political interest. A value of 2 reflects a person who's falling at sort of a medium or intermediate level of political interest. And a value of 3 is reflecting high levels of political interest. Just as a quick aside, I'm going to go ahead and say it. It's really generally a bad idea to take a continuous variable and chop it up in the way that I just did. But this was I basically did this in order to give me a new variable to work with that is categorical. So, but ordinarily I would not encourage this type of practice, but this was just to give me a dependent variable that is categorical for our discriminant analysis. So in this particular case, I've got political interest groups, if you will. So this is going to be my dependent variable. I'm going to basically be predicting membership in the low, medium, and high groups with respect to political interest. And then also I'm going to be using the predictor variables of dogmatism, external political efficacy, and consideration of future consequences. So these are going to be the predictor variables, and these are all essentially being treated as falling at an interval level of measurement and assumed to exhibit multivariate normality. Now, to carry out the basic analysis, I am going to go to Analyze, Classify, and Discriminant. So I'm going to put my dependent variable political interest into the grouping box, and I have to define the range. The minimum is going to be the lowest value that's in this column, and then the maximum will be the highest value. So basically groups 1 and 3 and are going to define the minimum and maximum values. Next, I'll put in my predictor variables. So I've got dogmatism, external political efficacy, and consideration of future consequences. Under statistics, I'm going to go ahead and ask for means, univariate ANOVAs, and boxes M. Basically, boxes M is essentially a test of the assumption of equality of variance covariance matrices between your groups. And what that basically translates into is that if you have equality, that means that the variances of your predictor variables and the covariances among your predictor variables are equal across the groups, and that's something that we do want. A violation can yield some inaccuracies in terms of some of your statistical significance results. So at any rate, I'm going to click on Continue, and under Classify, I'm going to go ahead and compute or ask for a summary table. So basically what's going to happen is that when I run my analysis, it's going to generate predicted probabilities for each case falling into groups 1, 2, or 3. And based on those probabilities, it's going to generate a predicted group membership. And so the predicted group membership is going to be related back to their actual group memberships, and so that the degree of correspondence between actual group membership and predicted group membership is kind of one way in which we can evaluate the fit of our model. So I'm going to ask for a summary table, and I'm going to also ask for compute from group sizes. I know that I had actually generated these groups in SPSS, but the group sizes are actually a little bit different. They're not exactly equivalent in size, and so if they were, I would just leave all groups equal, but in this case I want to compute the prior probabilities based on the actual group sizes, which are not exactly 100% equal. I can also ask for various plots if I want to, so I'll just click on those to kind of show you what they look like. Under Save, I can also ask for predicted group membership, discriminant scores, and probabilities of group membership. And so basically what happens is, as I said before, we take our predictor variables and we generate predicted group memberships. And the way that this occurs is that essentially each person obtains a discriminant score on each of the discriminant functions that are derived from the patterns of associations among our predictor variables. So basically from that, we generate probabilities of membership into groups 1, 2, and 3, and then based on that, then there's the program assigns people to a predicted group membership. So anyway, we can kind of take a look at what this stuff looks like when we run our analysis. So at this point, I'm going to click on OK. And what we can see right here, we had 161 valid cases for our analysis, and basically, when we scroll down, you can see we've got our group statistics. You can see that we have means and standard deviations and the valid sample size using listwise deletion for each of our groups on our variables. So you can see that we had 57 cases that were in group 1, 51 cases that were in group 2, and then 53 cases that were in group 3. So again, that further justifies our decision when we ran our analysis and we were asking about the prior probabilities that we were going to use compute from group sizes, because those group members sizes were unequal. So then when we look at the test of equality of group means, this is basically a set of one-way ANOVAs comparing our 3 groups on dogmatism, external political efficacy, and consideration of future consequences. So you can see the test comparing groups on dogmatism, there were no significant group differences, but we did see significant group differences on external political efficacy and consideration of future consequences. Mind you that these are just, like I said, basically one-way ANOVAs, and these would be the same ANOVAs that would follow from a one-way MANOVA, and looking at the output in SPSS, the test of between subjects effects. So it's the same information. Now when we scroll down, we can see we've got our boxes test. So this is a test of the assumption that our variance-covariance matrices are equivalent across groups. So the null hypothesis is that there are no differences, and that would actually be a good thing. So finding statistical significance is not exactly what we want to occur with respect to our boxes test. And so in this particular case right here, you can see the p-value is less than 0.05, sort of the conventional threshold for rejecting the null. So that would actually suggest that we have potentially a violation of our assumption. Now, keeping in mind that our sample sizes were roughly equivalent across the groups, maybe I'll find a little bit less concern over that. But when you violate the assumption, there's a possibility with respect to our significance test of making type 1 or type 2 errors. We're not going to get into the nuts and bolts of all that, but again, this is indicating that there is a violation of this particular assumption. We also do want to keep in mind that the assumption, the boxes test, is impacted by multivariate non-normality among our predictor variables, and it's also affected by sample size. So those are other considerations to keep in mind when you're evaluating whether or not a violation has occurred. Also, I do want to point out that discriminant analysis is not the only test that we could have utilized when our data was kind of fitting this particular structure. We could have also utilized, if we had a dependent variable with two groups, we could have utilized binary logistic regression. With 3 or more groups, we could have utilized either ordinal logistic regression if our DV levels are ordered, or multinomial logistic regression in those cases where we have unordered categories on our dependent variable. But nevertheless, we're sticking with discriminant analysis and going to punch forward with our discussion of the results. So we have right here, first of all, we have a summary of discriminant canonical discriminant functions. So keep in mind that the discriminant functions are essentially latent variables that are derived from the pattern of associations among our predictor variables. So we had 3 predictor variables. I'm just going to call them really quickly variable 1, variable 2, and variable 3, respectively. And so essentially what happens is that the information from these variables is combined to create discriminant functions. So discriminant function, so in this data analysis here, we actually had 2 discriminant functions that were derived. And each of the discriminant functions are derived such that they're related to our predictor variables, but they are uncorrelated with each other. So this is discriminant function 1, this is discriminant function 2. And so the number of discriminant functions that can be derived from a set of predictors is basically equal to the minimum value where we compare essentially the number of predictors P against the number of groups, or J groups, minus 1. So whichever is the least. So in this case, we had 3 predictors and we had 3 groups. So we had 3 groups minus 1, so that's 2. So the number of discriminant functions that that are derived is going to equal 2, and so that's what we have. If in our previous example in video 1, we had a circumstance where we had 3 groups and 3 predictor variables, and we had 2 groups, so that would be 2 minus 1 is 1. So in that particular case, we had 1 discriminant function that we were looking at. But in this case, we have 2 discriminant functions that are derived from our set of predictors. And then essentially we want to look at the relationship between our discriminant functions and our grouping variable, our categorical grouping variable. So this was our DV, if you will. Essentially, we can evaluate these relationships in a couple of ways. First of all, when we look at each of the individual discriminant functions and their relationships to the DV, you can see in line 1 right here, you get an eigenvalue, which is basically a variance estimate, basically kind of indicating the amount of between group variation on the DVs, or excuse me, on the predictor variables that's being accounted for by this particular function. Perhaps a little bit more useful from an interpretive standpoint is the percentage of variance. And so basically this is the percent of between group variation with respect to the predictor variables that's accounted for by the first discriminant function. So the first discriminant function is accounting for approximately almost 95% of the total between group variation with respect to our predictor variables. So you can see it's doing a lot of work. Then we have the cumulative percentage, which in the first line is just basically going to equal the percentage. And then we have a canonical correlation. And so the canonical correlation is a correlation between our discriminant function and the categorical or grouping variable. So it falls on a range between 0 and 1. And basically the magnitude is interpreted pretty much like we would interpret a Pearson's correlation. So in this particular case, function 1 is pretty highly correlated with our dependent variable. Okay, so what that means is that that we have a good bit of group separation with respect to discriminant function 1. When we look at function 2, you can see this is the variance associated with that particular function, and it accounts for about 5.1% of the total between group variation for the predictor variables. And so, as you can see, when you add those two, the percentage of variance from function 1 and 2, it adds up to 100%. So you can see that, with respect to the total association between the predictor variables and the dependent variable, essentially function 1 is correlated very highly with the grouping variable, and it's doing most of the work in terms of the variance accounted for between the groups. Function 2, the canonical correlation, is 0.15, and so that's, it's a very low correlation, and so there's less group separation with respect to that function. So it's actually doing less work. So at any rate, and it's important to keep in mind that the functions, as I said before, the functions are derived to be uncorrelated with each other. So we're taking the patterns of correlations among our predictor variables, and we're deriving uncorrelated latent variables, which are called discriminant functions, and we essentially are looking at those discriminant functions as they relate to the DV. And so we're trying to kind of explain the overall pattern of between group variation with respect to our predictor variables by way of these latent dimensions called discriminant functions. So the next step in evaluating our model then is breaking down which of our discriminant functions are significantly related to the DV. Now keep in mind, as when we look at our percentage of variance accounted for, if we had function 3, we would even had a smaller amount of variance accounted for. So each function that is extracted accounts for less and less of the total between group variation with respect to our predictor variables. So it's no big surprise, so the canonical correlations will exhibit this kind of relative ordering. So basically, ordering of 1 and 2 in magnitude, there would be a 3 in magnitude, and so forth for any subsequent functions. So testing our functions. So we have Wilks lambda tests with respect to our functions, and when we have more than a single function, we basically are utilizing what's called a peel-off procedure in trying to test those functions. So basically, the first test that we have is a test of functions 1 through 2. So it's looking at the combined effect of functions 1 and 2 with respect to the DV. So it's looking at the total between group variation accounted for by our predictors. So, in a nutshell, what that means is that we're testing, like I said, the simultaneous effect of these functions on on our DV. And so we're basically addressing the question of the overall relationship between our predictors and the DV. And so the significance, the Wilks lambda value that you see right here is actually the same Wilks lambda value that you would see if you ran a one-way MANOVA where we had our political group interest grouping variable as the IV and the predictor variables from our discriminant analysis as DVs. So because it's basically testing the overall relationship between the independent variable and DV. So we have a significance test. And so what this is telling us is that as a set, functions 1 and 2 are significantly related to the DV. So that's telling us then, again, that basically our predictor variables are related to the grouping variable. Okay? But we're essentially looking at that relationship via these discriminant functions. Okay, so our discriminant functions are related. So then we peel off the first function, leaving only that total between group variation that's accounted for by function 2. So essentially then, this next test, it says test of functions 2. So this is basically a test only of the function 2 right here. And we find that this was actually non-significant. So what that tells us then is that really function 1 is doing all the work, and function 2 is just kind of along for the ride. It's not really doing anything for us in terms of helping to explain the total between group variation with respect to our predictor variables. Mind you that at this point, this is really the function that we want to concentrate on in terms of trying to understand what is going on with this particular latent variable. And that would entail naming the discriminant function and so forth, which we'll talk about in just a second. But I do want to point out that, let's say we had three functions. Let's say that our number of groups had been 4, and we had 3 and 3, in which case we would have had 3 discriminant functions. In that case, we would have had canonical correlations for functions 1, 2, and 3. We would have had right here a test of functions 1 through 3, then 2 through 3 after peeling off function 1, and then we would have had a test of function 3. So it's conceivable that we could have had test of functions 1 through 3 being significant, and 2 through 3 being significant, and 3 being non-significant, in which case we would have been talking about functions 1 and 2. So that's just to highlight sort of the logic of this peel-off procedure in a little bit more detail. So at any rate, at this point, what we are finding is that we really want to interpret now function 1, because we know that really function 1 is driving the association that we see between our predictor variables and our grouping variable, our DV. So we want to name that particular function, and we can do that by looking at our standardized canonical discriminant function coefficients and our structure matrix. So basically, we're using these matrices pretty much the same way that you would interpret factors in factor analysis. So the structure matrix is basically giving you the zero-order correlations between each of our predictor variables and discriminant functions. So again, we had functions 1 and 2, and really function 2 is not significantly related to our grouping variable. So I'm just going to chop that out altogether. I'm not going to pay attention to that because that doesn't help us in explaining the relationship between our predictors and our grouping variable. So what I can do at this point is look at these correlations between each of my predictor variables and the function and give that function a name. So we see that external political efficacy is highly positively correlated with function 1, followed by consideration of future consequences. And you can see that dogmatism is not particularly related to that particular function. It's correlated even slightly negatively with that function. So, I might, based on, these two kind of marker variables, if you will. I might name this function something like, I might just keep it as external political efficacy, because I might think, well, maybe people who have more efficacy are also more future-oriented. So I might just kind of keep it named something along those lines, maybe even something like future-oriented political efficacy, just to give it a name. So, so at any rate, I'm naming my function. And then also I could go even further in naming it, or even just talking about the relative contributions of the predictors to that function. So these standardized canonical discriminant function coefficients are analogous to beta weights in regression analysis. So it gives you an idea about the relative contributions of our predictors to predicting group membership. So you can see that what we have for external political efficacy, this is the relationship between external political efficacy and function 1 while parceling out or controlling for dogmatism and consideration of future consequences. And so you can see it's a high positive predictive relationship. When we look at dogmatism and function 1 controlling for efficacy and consideration of future consequences, we end up with a slightly negative relationship or predictive relationship, and it's very, it's obviously very weak here. And when we look at consideration of future consequences relationship to function 1 controlling for the other two predictors, you can see it's very weakly positively related. So really, function 1 is largely being defined by external political efficacy, followed by consideration of future consequences and dogmatism. But it's really external political efficacy that's really doing most of the work in terms of defining that function. So I'm actually pretty good with naming this function, something like future-oriented political efficacy, or maybe even just political efficacy by itself. So in terms of so at this point, what we can say is that we have now found that there's one discriminant function that helps to explain group separation on the with respect to the predictor variables, and we're going to name that discriminant function future-oriented political efficacy. Like I said, if the second function had been statistically significant, then we would have also spent time naming that second dimension, but that was not the case, so there was no real point in doing that. So I want to kind of also show you that we have functions at group centroids. So, basically, it's like this, that we have essentially function 1 along the x-axis and function 2 along the y-axis. So the group centroids are basically multivariate means, if you will. And so basically you can see that we can actually plot out the group centroids relative to an origin of 0. So you can see that for group 1, function 1, the multivariate group mean, or centroid, if you will, is negative 0.824, which would be in the negative direction, and slightly positive at 0.068. So it'd be, I'm just sort of, I don't have a scaling on here. I'm just sort of giving you sort of the relative positions of these plots of the centroids. When we look at group 2 on function 1, the multivariate, or basically the group centroid, is 0.176 and negative 0.216 on function 2. So again, this is basically discriminant function 1, which we had already named as external political efficacy. This is discriminant function 2, which we didn't give a name because there's not really much separation on that particular dimension. And then when we look at the third group, we have 0.716. So basically what we have is a little bit higher here and positive, and so you can see that there's more separation horizontally than there is vertically with respect to these centroids. So that's again reflecting the fact that we're having most group separation on discriminant function 1. That's why we care about naming that particular function. So kind of scrolling down a little bit further, you can see we got our prior probabilities for the groups. Again, we had unequal ends, so asking for when we went through our analysis and under classify, it made sense that we were asking for computing the prior probabilities from group sizes. Kind of scrolling down, I'm not going to really spend any time on the territorial map, but basically we have at the very bottom right here, this is the classification results, which gives us a better idea about how well our model fits the data. So how well are we predicting group membership? So, what we had asked for when we ran our analysis earlier was we had asked for several pieces of information. So, kind of going through this, we had asked for under save, we'd ask for predicted group memberships, discriminant scores, and probabilities of group membership. So that's what all this information is. And a lot of times you may not be interested in asking for this, but this is to highlight what's going on in the classification table. So we have right here, when I roll my cursor up here, you can see discriminant function scores for function 1, discriminant function scores for function 2. Okay, so basically these are the scores on those discriminant functions that are assigned to each case in our data set, and it's based on those discriminant function scores that essentially probabilities are generated regarding group membership. So you can see right here you've got probabilities of membership in group 1 for our analysis, probabilities of being in group 2. So you can see like the first case right here. And then you also have over here you've got the probabilities of being in group 3. So you can see that case 1, the probability of being in group 1 was 0.46. The probability of being in group 2 is 0.34. The probability of being in group 3 is 0.19. So the highest probability is of being in group 1. So that person basically was predicted then to fall into group 1. The second person right here, you can see the probability of being in group 3 was the highest in relation to the probability of being in the group 1 and 2. And so that person's predicted group membership was group 3. So when we look at our table right here, you can see that essentially you've got our 3 groups. So these numbers right here are reflecting the actual group memberships in terms of falling into the low, medium, and high levels of political interest. So essentially, of the 57 cases that actually were observed to fall in the low interest group, 44 were correctly predicted by the model to fall into that particular group. So that would be a hit. That would be correct classification. So the accuracy rate for that is 77.2%. So 77.2% of the time, the model correctly predicted that a person would fall into group 1, and basically they had actually fallen into group 1. With respect to group 2, we had 19 out of 51 cases were correctly predicted to fall into group 2. So the hit rate, if you think of it, is roughly 37.3%. So we actually have a lower hit rate with respect to predicting group membership in group 2. And then with respect to group 3, you can see that 31 out of 53 were correctly predicted to fall into group 3. And so the hit rate is 58.5%. So the model does really the best job in terms of predicting who's going to fall into group 1. And the next best in terms of predicting who's going to fall into group 3, and the weakest job in terms of predicting who's going to fall into group 2. Now, on the with respect to these other values, you can see that we had 9 people who were misclassified as are predicted to fall into group 2, who actually were observed to fall into group 1, and we had 4 people that were misclassified as well. So 4 out of 57 were misclassified. So the rates associated with these 2 errors is 15.8% and 7%. So essentially, roughly 22% of cases were incorrectly classified as falling into group 2 or 3, when in reality they were observed to fall into group 1. So that's what these numbers are representing, are basically misses in terms of predicted group memberships in relation to actual group membership. So you can see that essentially this percentage right here is just reflecting the overall accuracy rate in terms of the predicted group memberships in relation to actual. So the model correctly predicted actual group membership about 58.4% of the time. But again, it did the best job in terms of predicting membership in group 1, and it did the worst job in terms of predicting membership in group 2. Just really quickly, as we were scrolling down, I drew this up earlier with respect to the group centroids. Kind of drew out my little 2D graph, but when we're looking at our output right here, you can see this a little bit better. You can see that for the canonical discriminant functions, it's got groups 1, 2, and 3. The group centroids are being represented. So there's, this is basically function 1. So there's, function 1. Oh, excuse me. Oops. Yeah, okay. Lost track just a second ago. All right, so basically we had function 1 kind of represented right here, and function 2 kind of going through here. And so as you can see, the group centroids, where they're plotted out, you can see that the greatest dispersion is occurring among the group centroids is occurring along discriminant function 1, and you can see that there's very little dispersion of the group centroids with respect to function 2. So at any rate, that pretty well concludes this illustration of discriminant analysis. Like I said, this is video 2 of 2 in a series. Keep in mind that these various statistical procedures, they do have assumptions about the data, and in those cases where your assumptions are not met, then that calls into question, well, what other options do you have available? Like I said, another option, if in those cases where discriminant analysis might be problematic in terms of meeting assumptions related to multivariate normality or homogeneity of variance covariance matrices, might be to utilize logistic regression. It's a much more flexible procedure. You can utilize categorical predictors, along with dummy coding in those analyses, whereas so you're not making those strict assumptions pertaining to normality as you are in the case of discriminant analysis. So those are just some things to kind of ponder kind of moving forward. So thank you for watching, and that concludes this particular demonstration.